Welcome. We are continuing our discussion on link budget, and we have seen that for a bent pipe transponder that C by N in the uplink, that is from ground to space, that is earth to space, uplink C by N naught in noise power density, or C by N if you take only noise power, and the downlink C by N naught or C by N, they can be put together to get the total C by N or C by N naught, and those relations have been found out, and this is true for bent pipe transponder. Let us look at it slightly deeper, because we just recollect first, that is, we have seen that C by, let us call N or N naught, both are same. Okay, let us put it as C by N naught, because we have seen till now N naught. Inverse of that of total is C by N naught of uplink and C by N naught of downlink. Remember that for this calculation, how it was derived, and when it was derived, numbers were not taken in dB, they were in ratio. So, though many times I go on writing this form in also in another form, you have to remember where it was dB and where it should be ratio. So, this calculation, if C by N naught is given in dB hertz, convert into C by N naught in ratio. So, let us write that this is in ratio, and the C by N naught of uplink was, if you try to recollect, it is EIRP of, since it is uplink, so EIRP from the earth station multiplied by G by T of, let us put it this way, then it will be easier to remember, of satellite, and then 1 by path loss or all other loss put together. Many times I will simply say loss or loss P, that is loss path, since path loss is dominating. So, it is, but since it is dependent on the frequency, so there has to be this case path loss in the uplink and the Boltzmann's constant. This is in ratio. When we put in dB, then the log version of this multiplication will become plus and inverse will become minus. Just remember that, since I am writing in ratio, so in this form let us look at it. So, C by N naught of downlink, similarly EIRP of satellite in this case, because it is in the downlink, and G by T of the earth station, it is the receiving, 1 by path loss, this time it is downlink, and of course 1 by K. And by getting the C by N naught uplink and C by N naught downlink, you can calculate the total C by N naught. But we have to see some more things into a little detail. This is a straightforward calculation, but since the things are power limited, we have seen that distance path loss is quite large. So, therefore, to manage the C by N naught to get a positive number in that and could get a good quality of service, you have to push in maximum power as possible. So, EIRPs have to be quite high. Now, satellites are generally nonlinear, and if this side is input, let us call power input, and if this size is power output, for low to high as you input goes to the satellite, this is characteristic of the any nonlinear power amplifier, but this is the characteristic of the total satellite, where the power amplifier is dominating. Now, you can see that at some point of the input, the output power is getting saturated, it is giving constant value. So, more increase in the input power, the output power does not increase. That means, if you go on increasing the uplink power, which is received by the satellite as a input, the output power will not increase linearly, it is getting slowly saturated. So, there could be a specification that at this point somewhere it gets saturated. So, that is the maximum power what the satellite output can give. We can correlate this thing, since the output power from satellite we have put along with the satellite transmitter antenna gain. So, we can call it equivalent to EIRP, and this is the input power which is coming, which is the we can equivalent to, we can put power flux density, which is coming as the input to the satellite. Similar curve will remain. So, input power flux density, this PFD you are familiar, earlier we have started with this. So, power flux density input coming to the satellite antenna, as we go on increasing, the output EIRP of the satellite will go on linearly first, and then it will saturate some point. So, this point we can call it EIRP saturation or saturated EIRP, and this point correspondingly the input which is saturating we can call as saturating PFD, or in short SFD, saturating power flux density. That means, the amount of power flux density which is coming at the input of the satellite, corresponding output of the satellite is maximum EIRP or saturated EIRP. Now, the spacecraft manufacturers, when they give the specification, they give like this. They said, for saturation EIRP, this will be the saturated, for saturating SFD, that is saturating power flux density SFD, you get a EIRP saturated value is like this. These two values are specified, that is the input point and that is the output point. Now, we do not like to operate in nonlinear region. We have seen simple nonlinearity, that it generates lots of spurious signals. So, therefore, we must operate in the linear region. So, the input maximum has to be reduced, that is from backed off from SFD. So, let us say this is the linear region we will be operating. So, corresponding input, that is PFD input, is backed off, it is backed off from the saturating PFD, which is SFD. So, it is called input back off, input back off, or IBO, input back off from the SFD. So, the corresponding PFD input is SFD minus input back off. When I say minus, these are all in dB. So, this is in dB W and this is also in dBW. So, but you can see, based on the slope of the curve, you can see that input back off correspondingly saturated EIRP is reduced by this amount. So, this is output, it is happening. So, this is called output back off. So, there is a output, I write it this way, output back off or OBO. So, the operating EIRP, at which at the operating point it is EIRP saturated EIRP or maximum EIRP, other way you can term it as maximum EIRP minus output back off, this is in dB. So, these are all dB values. So, we find out the operating point. Now, we let us try to correlate this uplink EIRP and downlink EIRP, or uplink C by N naught and downlink C by N naught in terms of saturated EIRP and in terms of the saturated power flux density, and that will be correlated to the operating point. So, we have to use input back off and output back off. So, let us try to do a jugglery on the calculation. I hope you have understood input back off and output back off condition. Let us do some jugglery of parameters, that is, let us see, EIRP was PT into GT in ratio. Okay. Now, I try to put this in terms of power flux density, that will be by 4 pi r square, and also I want to put it in terms of path loss, that is 4 pi r by lambda whole square. So, simply this PTGT can be written in this form, PTGT divided by 4 pi r square. I have introduced 4 pi r square. So, I will try to cancel it, 4 pi r by lambda whole square. I brought in lambda. So, I will cancel it, lambda square by 4 pi. You can see that r square is cancelled out, 4 pi, one of them is cancelled out here, one is remaining, that is get cancelled by this 4 pi, this lambda square getting cancelled with lambda square. So, these terms what I additionally introduce have a value equal to 1. So, PTGT remains, but then we try to interpret this term. This one is our power flux density, PTGT by 4 pi r square, and this term is our path loss, that is path loss 4 pi r by lambda whole square, and this is something new term. And let us see what is this term. This is related to the lambda or the frequency of operation, and it is spreading divided by 4 pi. So, we introduce a new term called S. It is something like spreading, we can call it a spreading loss, which is slightly different than path loss. So, it is a spreading. So, let us write it down. PFD stands for power flux density. This is known. L path is path loss, and this is we simply call spreading at a particular frequency, right. Now, this is in ratio. Okay. Let us write it in dB term. Then in dB terms it will be EIRP is equal to PFT input in dB plus path loss in dB plus the spreading in dB. So, C by N naught, whether up or down link, is equal to, if I remember in dB term, EIRP plus G by T plus, minus path loss minus K. This EIRP I replace by the additional term as PFD input, power flux density input coming, and then path loss plus the spreading plus the rest of the term is G by T minus path loss minus K. Now, this path loss and this path loss in this expression getting cancelled because plus minus. So, remaining term is PFD input plus S plus G by T minus K. Okay. These are all in dB. Okay. I started that this is in dB. remember that we have changed it. Now, this C by N naught could be in the uplink side or could be in the downlink side. Now, let us try to introduce our nonlinearity again, that is in terms of saturation power flux density and in terms of saturation EIRP. Let us try to express this. Let us recollect. This was our transponder characteristics and this was our SFD, saturation power flux density. This is power flux density and this side we take EIRP, and this is EIRP max or EIRP saturation, and if this is my operating point, this much is input back off and this much is output back off, right. And let us recollect, this is PFD operating point as input is SFD, saturation power flux density, minus input back off in dB, and sorry, this will be in dBW. Output input back off is in dB, and then EIRP, this is the EIRP operating point, is equal to EIRP max or EIRP saturation minus output back off in dB. Since it is EIRP, it is dBW. So, if we write for the uplink, EIRP is EIRP from earth station, EIRP from earth station is PFD input to the satellite, the loss in the uplink, that is mostly path loss and other losses added, that spreading in the uplink because it is dependent on lambda, the uplink lambda. So, therefore, it is equal to, I can write PFDI is equal to SFD minus input back off. So, saturation flux density minus input back off plus L up plus S up, right. So, correspondingly we can use this EIRP expression in terms of C by N naught uplink. So, let us write C by N naught of up is in dB EIRP of earth station plus G by T of satellite minus the loss in the uplink minus K. This EIRP will replace by EIRP of a station is SFD, saturation flux density of the satellite input, minus input back off of the satellite, that is operating point, L uplink and S uplink addition. So, then it becomes SFD minus input back off, then that L uplink is positive here, in the C by N naught equation L uplink is negative here. So, they get cancelled, then S uplink, then plus G by T of satellite and minus K. These are all in dB. So, the whole thing is C by N naught uplink is dB hertz. So, correspondingly we can write C by N naught of downlink is EIRP of satellite, that is operating point of the satellite, then plus G by T of earth station, it is downlink, minus L of downlink minus K. This EIRP of the satellite which is operating point, EIRP of the satellite which is operating point is EIRP maximum minus output backoff, EIRP maximum minus output backoff. So, we write here EIRP maximum, of course, from satellite, then minus output backoff is the actual operating EIRP of this is satellite, and this is of course satellite. Do not think of saturation, that is why I changed the word to max. So, output backoff plus G by T of earth station minus K. So, now this uplink is defined in terms of the, instead of earth station EIRP, we have defined in terms of satellite saturation power flux density minus input backoff, that is the operating point defined. And so, if we know from the specification of the spacecraft what is saturation power flux density, what is the maximum power flux density that can be given to the satellite, so that you have get a corresponding maximum EIRP. These two specifications, SFD and EIRP max at the satellite, if it is known from the specification, and if you can decide a operating point which is the linear region, which is input backoff and output backoff, then using these two expressions you can find uplink C by N naught and downlink C by N naught, and correspondingly you can find the total C by N naught. Okay, let us use this thing to do some quick calculation using some examples, very small examples I will give, and though I will try to give certain results also, that you should do your own calculation, find out if there is any mistake. If there is a mistake, you should correct that one. So, let us take one example, simple small examples to get you familiar with this type of expression. Let us call uplink frequency is 14 gigahertz, SFD of the satellite is minus 120 dBW per meter square, saturation flux density for the satellite. The uplink loss is already worked out and given as 209 dB. Find EIRP maximum to generate, EIRP maximum from the SFD given. This SFD given, what should be the EIRP maximum. So, in this we have to find out that S. So, the S that is spreading at 14 gigahertz, you can calculate, which was lambda square by 4 pi, and lambda you should know for 14 gigahertz. So, from that you can find out a number, it will be like minus 14.4 dB meter square. It was lambda square, so dB meter square. Now, it is converted into dB. So, EIRP maximum will be the SFD plus S in the up plus L up. L up is already given, S you have calculated up, and SFD is already given. Okay. So, therefore, you just put these numbers and you will get something like 44.6 dBW. Kindly verify the number. So, this is how, if SFD is given and frequency is given, you can find out the lambda, and loss is given, path loss. So, you can find out EIRP maximum from SFD. SFD to EIRP maximum can be found out. Let us take one more example. This is a small one. Here also let us take uplink frequency as 12 gigahertz. SFD is like change in SFD 91.4 dBW per meter square. Now, we are introducing IBO, input backoff, as 11 dB. That means your operating point is 11 dB lower than the saturation flux density, and G by T of the satellite is minus 6.7 dB per K. Then find C by N naught up. So, let us rewrite the C by N naught of uplink will be the saturation flux density minus the input backoff and plus S in the up plus G by T of the satellite minus K. So, S value will be same as the previous problem. So, minus 44.4 dB meter square, and this K value Boltzmann constant, we have seen this as a number. If you convert into dB, it will become minus 228.6 dBW per K per hertz. Remember this number, minus 228.6 dBW. This K is coming in all the C by N naught calculation. So, when you are operating in dB, when you are calculating in dB, you have to remember this number very clearly. So, C by N naught up, you can put all these numbers, S is known, rest of the things are given. So, you will get something like 75.1 dB hertz. Okay. I will give one more example quickly. I will just write it down, that frequency of uplink is 6 gigahertz, frequency downlink is 4 gigahertz, SFD is minus 67.5 dBW per meter square, EIRP maximum from satellite is 26.6 dBW, input backoff is 12 dB, output backoff is 5 dB, G by T of satellite is minus 11.6 dB per K, G by T of earth station is 40.7 dB per K, and loss in the downlink is 196.7 dB. Find C by N naught total. Since the uplink C by N naught and downlink C by N naught both has to be calculated, you get the all the numbers. One thing you will be surprised that L uplink is not given, and in our equation for C by N naught uplink with the modified equation in terms of SFD and IBO, L uplink is not appearing. So, that is not required. G by T for both satellite and earth stations is given, SFD and EIRP max is given, input backoff and output backoff is given. Frequencies are given so that you can find out S, and SFD is already given. So, it is easy to calculate the C by N naught total. You can do it in dB, it is much easier, but when you go from C by N naught up to C by N naught down to total C by N naught calculation, then it is better what you get in C by N naught up in dB convert into ratio, C by N naught down convert into ratio, and then do the calculation for C by N naught total, convert back into dB hertz in the total. Okay, thank you very much. We will continue our discussion in the next period. Thank you.